And so this water does play a strong role in the planet's evolution. And what I want to talk about is the early influence. Okay. And in particular, how the water is getting into the interiors of these planets, the influence it has on the atmosphere and the early evolution of these planets. And so I'm going to talk about magma oceans. Magma oceans are one of my favorite subjects. We sort of infer that there were magma oceans on many of the planets in the solar system, but we don't actually have a lot of direct evidence for it. In fact, the one object that we have pretty robust evidence for magma oceans is the Earth's moon, and that is based on the composition of the lunar crust. We infer that the Earth probably had a magma ocean as a result of the giant impact that created the moon, but we don't have a lot of geochemical evidence that it did in fact happen. Most of the evidence for the Earth would be, again, inferences based on models for core formation, separation of metal, which is a lot easier to do in a more liquid silicate, where you can allow equilibration of trace metals between the silicates and the metals. For Venus, it's completely uncertain, and a lot of models for Venus really depend on whether it has a magma ocean early in its history, because that kind of dictates the evolution of water on Venus. Now, Venus could have had a magma ocean in two ways. It could have had a magma ocean caused by a giant impact, similar to the Earth. But some recent core formation models are suggesting that for various reasons, they posit that Venus may have missed out on a late energetic impact like the Earth did that created the moon. And so maybe it wouldn't have had that kind of magma ocean. And then the other kind of magma ocean Venus could have had would be generated by the runaway greenhouse effect. So if it has a substantial amount of water and it is receiving more stellar insolation than the runaway greenhouse limit, that would drive the surface temperature to very extreme values and potentially cause melting of the surface. But that runaway greenhouse limit really depends on the evolution of the early sun. And that is still at this point kind of uncertain. And Venus has always been sort of on the boundary of where you might expect the runaway greenhouse limit to be in the early solar system, because while Venus is closer to the sun was also a little bit dimmer back when the planets were first forming. And now Mars seemed to have formed very rapidly. It might in fact be a protoplanet or an embryo, and I think Steve Desch might talk about this a little bit. And so that rapid formation, where you are acquiring a lot of accretionary heat really quickly, might generate at least a partial magma ocean, but we don't know for sure if Mars fully melted. And short-lived radionuclides, because Mars did form very rapidly, might have actually played a role here, whereas Venus and Earth probably formed in a long enough period of time that they didn't play a significant role in the heat budget. And rapid accretion may also be necessary for Mars to melt in a significant way. And then exoplanets, since we're here talking about exoplanets and solar system analogs for them, there's a variety of ways for exoplanets to acquire magma oceans. There's many planets that we have observed that are well within the runaway greenhouse limit. Some of them have so much stellar insolation that they don't even need an atmosphere to melt. There's just that close to their star. But as Vicki talked about this morning, even M-dwarf habitable zone planets may have experienced sort of extended runaway greenhouse driven magma oceans early in their history because of the way that M-dwarfs evolve. And so their habitable zones actually migrate inwards over time rather than outwards. Within the solar system, people have studied this, and particularly trying to understand the dichotomy between Earth and Venus. And this is work from Keiko Hamano from 2013, looking at the division between what she calls type 1 and type 2 planets, planets that retain their water during the magma ocean phase, and planets that lose their water during the magma ocean phase. And the division here is sort of based on orbital distance, as whether they can cool down quickly enough that their atmospheres can actually condense out. So these panels are a little complicated, but you can see over here on the left, we have type 1 planets. This is an Earth-like analog. What we have is the temperature evolution of the magma ocean in this panel here, showing how the magma ocean starts off at very high temperatures, 3,000 Kelvin, and drops down to this point here where this black area ends, and the magma ocean has solidified. And this panel down here is showing the partitioning of water between the various reservoirs, between the silicate melt, where it is very soluble, between the atmosphere, where it's existing as water vapor, and in the solid mantle, where it partitions to a lesser degree. It likes to stay in the melt and the atmosphere more. But we can retain some amount of water in the mantle. And in this case, the planet is cooling off quickly enough. Now water starts to condense, and we have sort of a magma ocean lifetime of a few million years, around 5 million years in this case. And then for these type 2 planets, you can see that the magma ocean lifetime here is about 100 million years. And what's going on here is that this model also includes, in addition to the magma ocean, it includes some degree of atmospheric escape. And we're going to hear more later in the session about different kinds of escape, but the kind I'm going to focus on here is specifically energy-limited escape, and it's driven by stellar XUV radiation. So this high-energy radiation is hitting to the top of the atmosphere, causing water to photolize, break up into hydrogen and oxygen, and at least the hydrogen is escaping and maybe some portion of the oxygen as well. So in this case, for this Venus analog planet, the planet is maintaining a very high temperature for up to this 100 million years. You can see the water reservoirs here. Most of the water remains in the magma ocean. And in fact, at this point, the magma ocean ends up solidifying because we have lost most of the water budget. And so, in fact, the magma ocean freezes only because we lose water. In other cases, if this model did not allow for atmospheric escape, this planet might not solidify for a very long time. Now, this model has also been applied by various groups. Luger and Barnes, that Vicki alluded to earlier, did this kind of modeling for habitable zone M-dwarf planets, and looking at this effect where you have this extended pre-main sequence lifetime of M-dwarfs that causes these habitable zone planets to be quite hot during their early history. And what they found is doing this kind of model, like the Hamano model, you get a lot of hydrogen to escape, but you can potentially build up a lot of oxygen. But one way you can get around having massive oxygen atmospheres is to get that oxygen to react with your magma ocean by reacting with iron. So you have iron 2+ takes up 1 oxygen, iron 3+ takes up 1.5 oxygens, and so you can absorb some of your oxygen into the melt phase in that way. And so we did look at this for a variety of exoplanets, including several that are not in the habitable zone. They're definitely in the runaway greenhouse limit. But Robin Wordsworth also took a model like this and applied it to more habitable zone planets to look at what kind of parameters this atmospheric oxygen buildup was sensitive to. And this figure shows the amount of oxygen you build up in the atmosphere as a function of the initial water in the planet and the initial iron oxide in the planet's mantle. So this dictates how much oxygen you can draw out of the atmosphere, and this dictates how much oxygen you can produce. And the factors that this was most sensitive to were the orbit of the planet, and the planet's albedo, and the planet's mass. So larger planets generate a lot more oxygen just because they have a larger reservoir, but their mantles are also a lot larger, and so they can absorb more oxygen into the interior. Albedo, if you increase the albedo to larger values than our nominal value, which was, I think, 0.3, and then you reflect more of the light, you drive less photolysis of your water vapor, and so you produce less oxygen overall. And then in terms of orbit, if a planet is further away from the star, it's receiving less insolation, and so overall you get less oxygen buildup. Now we applied this to another planet that was also in the runaway greenhouse limit. It's not a habitable zone planet, but we wanted to see how much atmosphere this planet could lose, whether it could retain an atmosphere. And for this planet, this is LHS 3844b. It was actually followed up with the Spitzer telescope. It was the first Spitzer thermal phase curve of a test planet. And this is the phase curve here, and you can see secondary eclipse is perfectly centered on this phase curve. And so we have a very nice symmetric phase curve with the hottest spot at the substellar point, the coldest spot on the night side. And so it seems like this planet is exhibiting essentially no heat redistribution, and so we think that this planet has really no atmosphere, and that's consistent with the atmospheric escape models. And so this is, again, using just a water vapor magma ocean model, the one I showed you previously, where we're looking at what kind of atmosphere could be left that was still consistent with the observations of the phase curve. And so the stable atmospheres produced by this energy limited escape model are shown in the colored areas, and the regions that we can exclude based on the thermal phase curve are shown up here, and regions that we can exclude based on very simple models for stellar wind erosion are down here. And so the only allowed region was really this parameter space here, and this is in terms of the initial water inventory of the planet would have only been about around an Earth sort of inventory. And this is looking at the XUV radiation fraction. It would have had to be quite low, a very low and not very active star early in its history. We applied this model also to oxidation of Earth and Venus to look at how much oxygen you could produce on these two planets, how much water you could lose. This is looking at the loss of water, where this is the initial amount for both Earth and Venus. You can see Venus loses a significant fraction of its water, usually up to 95%, and Earth is only losing a tiny fraction of its water. And then that oxygen is going into the mantle, whatever is being produced, and is oxidizing the mantle. So this is showing the production of oxidized iron in the mantle as it is solidifying. So you can see the red curves are Venus for different initial water abundances. And we get a fair amount of oxidized iron produced on Venus, which is consistent potentially with the observation of the inference that Venus's surface might be relatively oxidized. But for Earth, we don't produce very much. And it's certainly not enough to produce present-day oxidation levels. So this does, of course, depend on what we know about the early sun's history. And there has been recent discussion of whether the sun is a slow or a moderate or a fast rotator, and that dictates the level of high-energy radiation that the planets receive early in their history. And just briefly to discuss Mars' Magma Ocean, this figure here is from Saito and Kuramoto, and it shows that the surface temperature of the planet as a function of accretion rate for either a half a Mars mass or 1 Mars mass. And you can see in order for the planet to actually get into a magma ocean regime, you have to have extremely large volatile abundances, up to 4 weight%, or extremely rapid accretion rates. And so whether Mars had an early magma ocean or not, I think is kind of still to be determined. I just want to finish up. I'm not going to get to the tectonic models, but I want to finish up by talking about sort of the higher region of planetary parameter space, that sub-Neptune region of that bimodal distribution of planets that Vicki showed this morning, on the larger side of the Fulton Gap. And these are sub-Neptunes or mini-Neptunes. And this model is just showing the temperature of the mantles of these planets, where they have some large fraction of hydrogen envelopes. And you can see that these planets are all relatively hot in their interiors, especially early in their lifetimes. So the interiors of most of these sub-Neptunes are silicates, and they're actually molten silicates. And because volatiles are soluble in molten silicates, that has implications for the atmospheres of these planets. So this is work that Edwin Kite has led, and it's actually accepted now and available on the archive. And what we're looking at is the distribution of volatiles between the atmosphere and the interior of these sub-Neptune planets, depending on whether you start with hydrogen and produce a little bit of water, or if you start with a lot of water and produce a little bit of hydrogen by reactions in the interior. What you can see here is that the dark colors here are the volatiles that are within the magma ocean itself, and lighter colors are volatiles that are in the atmospheres. And these are log scales. So what you should take away from this is that most of the volatiles, 80 to 90% of these volatiles, are in fact in the magma ocean. So for these sub-Neptune planets, it is important to realize that that atmosphere interior boundary is not a fixed impermeable layer. There's interaction going on between those different reservoirs that's going to control or influence certainly the evolution of these planets. In particular, if you're looking at photoevaporation models of these planets, you have to lose a lot more hydrogen than you might have initially thought because you will get continuous outgassing as you strip off the atmosphere. Okay, and so I think I'm out of time, so I'm going to skip to my conclusions. So in summary, a lot of planetary volatiles will interact with the interior. We didn't discuss any atmosphere and solid reactions, but obviously carbonate silicate cycling is a very important climate controller on rocky planets. But these kind of things have a very strong influence on the early evolution of the planet. And exoplanets really occupy a much wider parameter space than we see in the solar system. And so we have to ask at what limits of planet size and volatile composition these models we've developed in the solar system can really be applied to exoplanets. So thank you.